Hello, I'm Professor Seth Chandler from the University of Houston Law Center. Today's video is on symbolic regression. It's part of the course Analytic Methods for Lawyers. Symbolic regression uses an analog of evolution in order to find predictive models. The key idea is to represent mathematical expressions, formulas, in ways that can evolve through what is the equivalent of sexual reproduction, where only the fittest models get to mate. Now, when you add mutation, occasionally, to this mix, this method of symbolic regression, a form of genetic programming, works incredibly well in developing models that fit well and that often have a high degree of explainability. Symbolic regression is used in serious industrial applications, and what's nice is it can also be used as an adjunct to other statistical and machine learning techniques such as conventional regression. It's also exceptionally useful in figuring out which variables matter in a data set or which combinations of variables in a data set really end up having an effect. A note before I begin. In every other video that I've done for this course, it's been basically vanilla Wolfram language. I haven't used proprietary packages. In fact, I'm not even sure I've used any packages at all. This video needs to be different because symbolic regression is not directly implemented in base Wolfram language. Instead, I'm going to be relying on a commercial package called Data Modeler, to which I've got a license. The package is immensely powerful. It's used by big, large corporations to do their data modeling, and so it's so good that I've decided to make a little trade here. Normally I like everything to be transparent and reproducible. Here I'm going to sacrifice some of that transparency and reproducibility in order to better illustrate a concept and its practical implementation. So you're not going to be able to replicate all the code in this notebook. Instead, you can look at it and appreciate it and hopefully understand the ideas of symbolic regression as well. Okay, here really is the key point. Mathematical expressions are trees, or at least you can visualize them as trees. Here's a symbolic expression. Okay? Let's show what it looks like as a tree. The idea is it's a sum, and the sum is of C and some product. The product is of A and Q. And so we're representing this as a tree, and to figure things out, if these were real numbers, you might first do the multiplication, take the result, and add it to C to get your final answer. Okay? Here's another mathematical expression. This is our friendly logit. And let's look at the tree form of the log of the odds. Okay? And you can see that its head is log, and then we're going to take the log of some expression. That's a product, a times. The times has two parts. One itself is a power. But why is it a power? Because all you see is division. Well, division is sort of taking something to the -1 power. And so again, it's a tree. Next piece. These little subparts of the expression, they're trees too. There's just subtrees. So we can look at the first part of the first part of the first part of this expression and look at it, what it looks like in tree form. And here it's 1 plus -p, which is 1. We would say that's 1. We would say this is 1 minus p. But to the machine, no. It's plus of 1 and then the product of -1 and p. Okay? Here's something else. Here are two expressions. Okay? Both can be represented as trees. Now, supposing I took the 1, 1, 1 part of the left expression, 1, 1, 1, and I took the 1, 2 part of the right expression, and I snipped, and I snipped, and I swapped them. Basically, here's what I'm going to swap. And this should be the 1, 2, 2 part. Yep. All right. I'm going to swap them. And here's what they look like. To do the swap, I'm going to say take your original expression and take the 1/1,1th part and replace it with the 1/2,2th part of the second expression. And take the second expression and replace its 1/2,2th part with the thing that you just snipped off here. Okay? So let's see what that looks like now that we've mated. And we've made two new expressions, but they have elements in common. There are like genes here that are still here. Okay? So that's the idea of crossover, of propagation through crossover. We've snipped and we've exchanged and glued the parts back on. Now, what's cool about mathematical sex is it doesn't have to be binary. You could have a rotational scheme in which you snip person 1's fragment, you attach it to person 3, you snip person's 3 fragment and attach it to person 2, and you snip person 2's fragment and you attach it to person 1. So you can have threesomes when you're doing a mathematical propagation. And you can even, you can mutate trees randomly. That's another thing you can do. So let's look at all the places where we might mutate a tree. Let's get all of the positions in our tree. Don't worry about positions that start with 0. All right, so here are all our positions in our logit tree. And now I'm going to pick one through random choice. Well, I picked the only one that wouldn't work so well. Let's pick something again. There we go. I like that much better. And now what we're going to do is we're going to take our original expression, we're going to take this part, and we're going to replace it by e to the negative 2p. And so we get a new expression. We could take the tree form of that. And there's our new expression, and it's tree. And so mutation is also a propagation operator. Okay. If I combine mating with mutation, that is really close to how biological evolution proceeds, at least sexual biological reproduction. You just have to think of the trees as chromosomes, and the swapping that I described is the equivalent of crossover. And so if this theory is right, and evolution is actually correct, then if I only let the fittest trees mate, and by fit, I mean perhaps they predict something well, or they do something I want well, then if I let them mate, in theory, the system should evolve through survival of the fittest, or sometimes celibacy of the least fit, to start producing expressions that end up doing even better. And yes, some of those evolve, some of the kids will be not very useful, and most of the mutations will be bad. But just like in nature, if we have enough mutations and we have enough offspring, we might just get better and better trees, and if the job is prediction or classification, they might predict or classify better. So what I've described is what's sometimes called genetic programming. Instead of trying to write the program yourself, you create groups of random programs and you let them co-evolve until the programs are performing well. And you might think this can't possibly work, but it does. I'm going to give you a demonstration. Maybe some of you remember Newton's law of gravity. Here it is. This is the gravitational force between two objects, where we have one of the objects has mass m1, the other one has mass m2, and their distance r apart from each other, so we need to use, so we do use r squared, and we multiply it all by this gravitational constant that still people don't know the exact number, what that value is to a lot of decimal places. But in any event, that's our formula. But supposing we're not as smart as Isaac Newton, and we can't figure that out. What if we had symbolic regression at our hands? Could we, by observation, basically rediscover the Newton's law of gravity? So I'm going to make it a little tough for us, because we don't know that these are even the relevant features. Maybe what's important to gravitational force is the wavelength of light that's emitted, or maybe it's how many rings the planet has. So supposing we've got some data, we have the necessary data. That is, we have the mass of one planet, the mass of the other planet, the distance between them, but we also have the wavelength of light that's emitted from the planet, the diameter of the first planet, the diameter of the second planet, and the number of rings each planet has. So let's see if we can figure out the data. I'm going to make a somewhat tricky data set. Here's our function that creates the data, and it's a long, sort of tedious function. I don't really think you need to study it, but I'm going to make life a little hard for myself by saying, you know, the mass of a planet and its diameter are probably correlated. Yeah, it might differ depending on the density of the thing, but if you have a really big planet, it's unlikely, not impossible, but unlikely that its diameter is small. So we're going to create some data, and we're also going to create the possibility of it having noise in the data. Maybe our observations of the gravitational force are imperfect. Second argument is how many rows of data do I want, and the third argument is how do I want to seed our random number generator so this is replicable if we need it to be. All right, so let's evaluate our function, and let's now create some data points. I'm going to use, here it's going to be noiseless. Okay, if you want no noise, just do Bernoulli distribution of 0, and the result of that is always 0. I'm going to make 20 samples, and that's my random seed. So let's create some data. And I am going to export this. We haven't done anything on export, but I'm going to save it as a file because I may want to show you the graphical user interface for Data Modeler, and then we're going to need a file. All right. Now, let's load up the package. This is the Mathematica command needs, is what you do to get a package loaded in. What is this package Data Modeler? Well, it's from a company called Evolved Analytics. It costs $5,000 a year for an individual commercial license. It costs less if you're an academic, and even less if you're really, really nice to the lead developer. But it's a gigantic package with hundreds, if not thousands, of functions and options, and it has a really nice graphical front end that's going to make it easier to use. I'm going to try and demonstrate that briefly, at least, in this video. All right, so we've loaded up Data Modeler. Okay, loaded up, and lots of functions. The one I need is called Symbolic Regression. So I only need one little piece of code because Symbolic Regression tends to produce pretty big output. And so I'm going to use a built-in Wolfram language command called iconize that's going to sort of make a compressed representation of the output. So if I say iconize of range 100,000, it's just going to give me a little blip that if I expand it, it's going to tell me, hey, this is a list with length 100,000, and it takes 800,200 bytes to store it. If I click on uniconize, it will get the whole ghastly thing. All right, so that's iconize GP model. We're about ready to go here. Let's look at the form of our function. It's called symbolic regression. And you can imagine that the data, if we look at what is the structure of the data, it's a 20 by 9 array, 20 rows, 9 columns. It's like the data that you use for linear model fit or logit model fit, and it's not like the data that you use that comes out for machine learning, like Boston Housing or the Titanic, which is a bunch of rules. So what we want to do is we want to get the features and the target. There are other ways you can do this with symbolic regression, but I'm going to standardize on this method. So to get the features, what does most do? Most of range 7, for example, gets everything but the 7. Okay? Most of character range A to Z is going to get A to Y. So that's what most does. I think we've seen last already. So here we're getting the features, the independent variables, and here we're getting the dependent variable, the target, the label, lots of different names for the same idea. Okay? I don't have to tell it what the data variables are named, but I'd like to. It's convenient when I see formulas. So this is the mass of the first planet, the mass of the second planet, the radius between the planets, the wavelength of reflected light from one of the planets, the diameter of the first planet, the diameter of the second planet, how many rings does the first planet have, and how many rings does the second planet have. All right. And my final option is, I'm very impatient. I only want this to run for 30 seconds, and the rest of this is just telling it how to post-process the output. So I think we're ready to run. Here we go. Right? So what it's doing, it's going to take about 30 seconds, is it's generating mathematical formulae. It's seeing how successful they are in predicting gravitational force. If they're not successful, they're going to get discarded. If they are successful, they're going to have sex with each other, and they're going to produce new formulae. And there'll be an occasional mutation every once in a while, maybe about 5% of the time there'll be a mutation. And we're going to keep going through various...
248 models have been generated.
And isn't that nice? It tells you that it's done. And this is the form of the output. And I need kind of to explain to you what to see in this output. It looks pretty inscrutable at first. So let's look at a representative model. I'm just going to pick the 100th model, and I'm going to iconize it also because I don't want to see all the glop at the end. That can be very useful, but for beginners it's distracting. All right, so what do we have? The first part here, there are three parts. There's this part, this inscrutable part, and this part that I've iconized away. First part is a measure of performance. As it happens, the first number is a metric of how complicated the model is. Low is good. We want simple models. High is bad. The second is a measure of basically the error rate. It's 1 minus r squared. Low is again good. So this model is doing decently. That's an r squared of, what, 0.89. This next part here is sometimes called the model phenotype. It's sort of an encrypted version of the formula. And we'll show you how to get information out of it. But it's basically a compressed version of the formula. All right, so how do we get information out? Well, one way is model tree plot will actually sort of show you a picture of the formula, and model phenotype will show you the Wolfram language equivalent of the compressed formula. So let's run that. And there's our tree. It looks somewhat similar to tree plot. And here's our actual formula. And you can kind of understand it. Like this is a sum. Sigma is usually for sums. Here we've got negative 63.8, just like here. And here we've got the product of 72,244 and D1. And then we're dividing by R and we're dividing by W. So that's the concept. All right, one thing we can do, though, is we actually generated, remember, a whole bunch of models here when we did our symbolic regression. One thing we could do is to take a plot of these values, of the complexity and of the reduction in variance, the fraction of unexplained variance in the data. And to do that, there's a command called Pareto front plot. I'm going to run it and then I'll explain it. Okay, so here it is. You can see that there's complexity on the x-axis, and there is 1 minus r squared, fraction of unexplained variance, on the y-axis. And you can see these are 1 point for every model. If I mouse over a model, it'll tell me the phenotype for that model, basically, or the model expression. So here's one that says, oh, I think the formula is 66.14 plus 0.56 times the mass of the second planet squared divided by the cube of the radius. Okay? But you'll notice there are these red points here, and I can mouse over them, and I'll also get a formula. But what does a red point mean? A red point is on what economists and other people call a Pareto front, meaning there's no point that is better in both. There's no point that has both a better complexity, less complexity, and that explains more of the variance that's down lower. So this point isn't on the Pareto front because there are all sorts of values that are in this box here. And this point isn't on the Pareto front because there are all sorts of values that are better. But these values here in red, there's no way of improving on one without sacrificing the other. So a Pareto front's a very useful concept. We can actually ask it, hey, I just want the Pareto front. And then what I want to do is what's the quality and what does the expression look like? So let's actually look at this. And shouldn't take too much longer. All right, for some reason it took a little while. But in any event, here are formulas that are on the Pareto front. And here's one. It sort of has the right variables. It's got an M2 in the top and an R in the bottom. But if we get all the way down, let's look at this one. A complexity of 26, 0 unexplained error. And what's the formula? It's essentially nothing. We'll treat that as nothing. Plus 6.67 times M1 times M2 divided by R squared. And that, my friends, is Newton's law of gravity. So let me just emphasize what it did. It figured out from the data, without me telling it anything, what the relevant variables were, M1, M2, R squared, and R, and it figured out what the correct relationship was between those variables that fully explained the data. And it did this without any real guidance on my part. It just said, here are some models, go forth and propagate. And through genetic programming, it came up with the right answer. I think that's a remarkable achievement. And it's one of the strengths of symbolic regression is it does have the capability of finding mathematical models that really do represent your data. Why is it good to have a mathematical model? Well, we've had them for, centuries. We know what to do with formulas. So we can take their derivatives. Here we could say, hey, what's the derivative in gravitational force as I start to increase the distance? And so it gives me a formula for that, and that might be useful if I were trying to move the asteroids apart or together, or I was flying a rocket ship. In any event, we have hundreds of years of experience with what to do with formulas. Plus, if we have a formula, we can write a compiler. We can compile it into machine language code. So Wolfram does permit functions to be compiled. I'm not going to go through how exactly the compiler works, but let's just grab, well, here's our expression, and I'm going to compile it. Now this will take a few moments. The first time you run the compiler, it's got to do all sorts of interesting things. So I might pause and come back. Okay, we're done. It came back. We have a function. And now, let's make some data. We're just going to make the mass of 100,000 planet pairs, 100,000 first planets, 100,000 second planets, and a radius. So we'll do that. We have a 3 by 100,000 matrix. And now, let's apply our compiled function that we generated basically from as an output of symbolic regression and see how long it takes for our formula to evaluate 100,000 planet pairs. And I'll use repeated timing as I've done in one of the prior exercises so that we run it more than once and get an average. Okay, so it took 3/1000ths of a second on my little MacBook Pro, and not the M1 version that I covered either, to do 100,000 planet pairs. That is a great virtue of symbolic regression. Again, computers know how to do formulas, and so you can evaluate things really fast once you have the output from symbolic regression. What else can I tell you? Well, symbolic regression plays with both the statistics framework in Wolfram language and the machine learning framework in Wolfram language. So supposing I take the third to last model on the Pareto front and I say convert it to a fitted model, and I want you to use, here's the features and here's the target. So let's do that. And we get our friendly fitted model object, the kind of thing that we got when we did linear model fit and logit model fit way back when. And so now we have all the functionality of the fitted model available to us. So we could look at the parameter table, the ANOVA table. I think I did cook distances with you. And so we just get all sorts of great stuff once we have it in a fitted model. The output from Data Modeler can also play well with the machine learning framework in vanilla Wolfram language. Let's actually build functions from our various models that we found up here. Okay? We're going to turn these into function objects. So to do this, data variables is going to get the name of the variables, model phenotype is going to get the Wolfram language expression, and we're going to put those together. I don't think you need to understand the details of how that code works, but there we go, okay? And so if, for example, I were to take funcs, not that, funcs1, okay? And I were to apply that to I don't know, mass 1 is 3, and mass 2 is 4, and the radius is 5. I think that's all I need. I don't need to fill in the rest. It's going to, oh, it doesn't like that. All right, so I got to fill in the rest. 0, 0, 0, 0, 0. And it gives me an answer, okay? If I change this to 6, we don't get a different answer because in funcs1, the only thing that matters is the radius. So if we change that to 7, then I get a different answer. Okay, great. So let's see how the model works on data it's never seen before. So I'm going to create 500 new data points. I'll use a different random seed, no noise, and then I'm going to export that data to a file in case I want to show you how it works in the GUI. So let's do it. Okay. Now, let's actually generate the model predictions for each of the models on the Pareto front. Here's the code I'm going to use to do it. It's a little inscrutable, but the idea is we have all these funcs, right? We got all these funcs up here. And for each func, I want to take the features, and in fact, we could even make this code a little cleaner. Let's do this with features equal that. Yep, that's a little better. Okay, we're going to compute the features, and then for each func, we're going to apply that func at level 1 to the features. We've used apply level before, and you can look at the documentation on that function if you'd like. But when we do that, we get a 6 by 500 matrix. That's what we want. Because, why 6? Because there are 6 models on the Pareto front. Why 500? Because I made 500 data points. So these are the predictions of our models for each of the 500 data points. Now all I need to do is to say for each of those predictions, right there, compute the predictor measurements of those predictions and compare it to the last column of the test data, which contains the real value for gravity. And that will give us, if all goes well, 6 predictor measurement objects. And now I could, for example, take the third to the last predictor measurement object and look at a comparison plot or an R-squared value. And there we go. It is, oh, it's taking the last three models, I'm sorry. And so our third to last model is terrible. Our second to last model isn't very good on the Pareto front, but look at that beautiful picture. Our last model on the Pareto front, which you remember is the perfect model, all those points line up in a beautiful way, and an R-squared of 1. My main point here, though, is to just show you how you can integrate the output from data modeler and symbolic regression, and then use all the capabilities of the pre-built Wolfram language machine learning functionality. Another great thing about symbolic regression is you can use it, remember like Lasso, you could figure out kind of what data variables were important? Symbolic regression is great for figuring out what data variables are important so you can focus your energy on them. And to do that, let's create some noisy data this time. We're going to create 100 samples, and this time there's going to be noise in our measurement of the force. A disturbance in the force, as it were. Now, we'll run symbolic regression on our new data. Same data variables, still an impatient 30 seconds. And I'm going to run this, and we will come back in 30 seconds. Okay, 25 by my count, 26, 27, come on. Maybe I counted fast.
"289 models have been generated."
I just do it because I like to hear his voice. All right, we can generate a Pareto front plot of those new models. There we go. We see we've got some pretty darn good models here. And in fact, the one I just picked, you can see that is very, very close to the truth. It's got a little bit of a intercept term, that negative 0.24 thing there, and our constant for gravity is 6.68 instead of 6.67. So the noise is an issue, but by jinkies, it has found a pretty good model. We can look at the model quality and model expression as we did before for the models on the Pareto front. There we go. Lots of models. And as I said, there are actually models that predict better. Like here's one with a complexity of 117 with 2 1/millionths of the variance unexplained, and it's a very elaborate model. And in fact, what is this model doing? This model is chasing noise. It's got stuff that we know doesn't really matter, like the diameters or how many rings does the second planet have. It's a little bit of a problem, but maybe from studying this Pareto front and studying the models, we can try and figure out what variables are important. It's sort of like figuring out, what genes are important in determining whether you get cancer or whether you live a long life. So what we're going to do is we're going to use the select models function from Data Modeler to take all of those models. I'm going to say, hey, I only want models that have a complexity less than 100 and that can explain 80% of the variance. And I want to focus on models that are close to the Pareto front. You can read up on what selection size does more precisely. So we've got it looks like about 61 models there. And now we can make what's called a variable presence chart to see what variables tend to be present in the beta models. And you can see, hey, it's getting it right. M1, M2, and R are in the better models, and in fact, R is in all of the 61 better models. Now, it is true that D1 makes an appearance, and ring 2 makes an appearance, so does ring 1, but this is again saying maybe we should focus our energy on M1, M2, and R. Another cool thing we can do is make what's called a variable association graph plot, where it's going to show combinations of variables that tend to be used together. So this triad seems to be used together a lot, although sometimes M2 is used with D1, but ring 2 and D1 don't seem to talk to each other, and neither do ring 2 and D2. So what I might do now is I might decide to rerun the symbolic regression, but I figure, this W thing, it doesn't seem to be a big deal. D2, ring 1, ring 2, let's just get rid of them. And I'll keep D1 because it does seem to be popping up. So we'll rerun it again. Same code here. The only thing I've added is allowed variables. I'm restricting the variables that the models are permitted to use. So we'll run this for 30 seconds. I'll pause. We're back. I'm just waiting for our person to say it. Come on.
318 models have been generated.
All right. We can look at the models on the Pareto front. Oops. And we can again do another variable presence table to see, well, this is a little different. It's a different presentation, but it's telling you, look, R is in 95% of the models that are we've now generated. M1 is in 80, M2 is in 74, D1's really lagging behind. And so maybe D1 isn't that important, and now we can really focus on finding the functional form that best explains the force of gravity that we're observing. The other thing we could do is let me generate a Pareto front plot of these models that we just came up with. And what I might well do is focus my attention on models at what's sometimes called the knee, where, look, right here we're gaining a huge amount in predictive ability by just a little increase in complexity. But by the time we get over here, in order to gain anything in predictive ability, we're having to make big sacrifices of complexity. So often what you want is where you're at this, what's called the knee of the curve, and there's our great model right there. So focusing on the knee of the curve is often useful. I could also use select models to say, look, I only want to see models that have a complexity less than 30 and that explain 99% of the variance. And as it happens, that's the right model. That's Newton's law of gravity with a little noise in it. We've studied model ensembles before. We looked at random forests, which are a form of ensemble. We looked at boosting, which produces an ensemble of models. And symbolic regression and data modeler are very big on creating model ensembles. But the idea here is you want to pick your models like you pick your stock portfolio. You want models that perform well, yes, but you want models whose performance is actually uncorrelated insofar as possible with each other. And just as in the stock market, that tends to give you the greatest return for some level of risk, or the least risk for some level of return, so too, it makes sure that your models aren't off in deep space. You're not taking huge risks, but you're getting accuracy in actually coming up with mathematical models. So the data modeler function here is create model ensemble. We're going to restrict ourselves to decent models. We're going to give it some data. This is our original symbolic regression. Robust means I don't want models that like divide by 0 and do weird stuff. And the strategy for putting together the ensemble is I want the models to be uncorrelated. So there we go. We now have a model ensemble, which is wrapping a bunch of GP models. And now what we can do is we can make an ensemble prediction plot on data that it's never seen before. And let me just show you what this is. Okay, and this is showing you basically the bounds of the values that you get from your ensemble. So in some instances, these bounds are very high, and when you have these unusual cases where the prediction is very, very large, The error can be very large, but when you have models that, or values that tend to be reasonable low, then you can see that the variation among the models in the ensemble is not very great. The other thing we can do is to use the ensemble to see how does, we're going to just cut that out. How do changes in variables affect the predicted level of gravity? And this is done through a response plot. And you can see that it's showing you that as our M1 value deviates from our sort of reference value, that we're getting, reasonable bounds on what the true value of gravity is. But as we start to get far away, the breadth of possibilities increases, and you can see with ring 1 and ring 2 it doesn't matter because they're pretty much irrelevant anyway, so too with W, D2, D1, but you can also see that as the radius shrinks, we start to get very high variation in what our model is predicting, and that may well be because you're dividing by r squared, and so as r gets very small, the denominator is blowing up, and so little blips in the denominator could have a pretty big effect. So I'm going to stop here on the notebook portion of this video that discusses symbolic regression. We're going to come back in a moment and take a few moments to look at the GUI so you could at least see how sort of a data professional, what opportunities might be available to them. I'm now going to try and show you the GUI for Data Modeler, and I know this is a little challenging because the font is likely to be small on Camtasia. I'm having a little difficulty getting Camtasia to play well here, but hopefully you'll get the basic idea. Also, there's some preliminaries that I went through here that were sort of done off screen just because it's really impossible for me to do a screen capture of what I went through. But in any event, what we're going to do is we're going to select some variables, and we need to select what our response is, and what we're trying to produce is what we're trying to predict is force. I don't think there's anything we need for our data record label, and we're not going to be playing with variable sets yet. Well, we might select all the variables, and we could call that all variables. And we could spell it correctly. All right, and that's fine. We're now ready to explore our data, and you can see that it's producing a distribution plot of the various features in our data. Here's something I like. It's telling you where relative to 0 the points are falling. It's showing you, for example, that the values of rings are discrete. If we had missing data, we could learn about how complete the data is, but it's a big glob of green because I don't have any missing data. We could also look at the correlation between various features in our data set, and in just a moment we should see that, and that seems to have blown up, so we'll need to talk to our developer about that. We can see how well various variables correlate with force, and it looks like M2 is having a pretty decent correlation with force. Rings 1 is not. So there are all sorts of interesting things one could do here, but let's get busy on generating models with the GUI. And what we're going to do is I think I'm going to do 4 independent evolutions. We'll run this for 3 minutes. I don't want to emphasize linear models. We'll let all the variables be in there. I think this is what I need. And so we're going to start to see, if all goes well, a graphical look at what happens during the evolutionary process. All right, here we go. Press Generate Models, and it says it's going to start soon. Okay, so It's doing two at once because I only have two kernels on my little MacBook, which all this runs on. And what you're seeing here is basically this is how is the error evolving over time. And so one kernel is this is what it's finding, that it's managed to get the error down here. This other evolutionary path has managed to get it here. We can also see the Pareto front of the current evolution. So this is the trade-off that one of the kernels, the sort of olive kernel, has been able to achieve. And here's the Pareto front that the green kernel has been able to achieve. And if all goes well, we should see these things change as we move on. Now, if you notice, it's actually doing really well. It doesn't look like well, that may be our friend. Yeah, that's our friend, the perfect model, m1 times m2 divided by r squared. Maybe it hasn't yet found the constant, gravitational constant it needs, but that's a very promising development for us. And so let's just let it keep going. I have said 3 minutes, and so I think what I'll do is come back when we get a little closer to the end. All right, and so now we're seeing the third and fourth runs kick in. The kernels finished 2 runs, and now they're starting on new runs, and we can see what our accuracy looks like on these new runs. I don't know if I can move over. No, I can't. All right, we'll come back again when we get close to done. All right, we're into the home stretch here. We're at 5 minutes and 54 seconds, and you can see it's a little uninteresting because it actually found basically the perfect model.
292 models have been generated.
All right, and so one thing we can now do is we can analyze our models. And so, for example, here's our Pareto front. That's basically our perfect model there, but it turns out that just looking at the mass of the second planet and the diameter of the first planet, which after all is correlated with its mass, works almost as well, interestingly enough. We can look at things such as the dimensionality of the model. So let's click on that. And what we're going to see is that of models that here are models that use just one variable. What are they able to achieve? So we have the blue and red points are what you're able to achieve with one variable. And then this is going to tell us which variable it is. Then with 2 variables, we can do better. You'll notice there are fewer grayed out. Well, we're moving closer to perfection here. With 3 variables, which is what our perfect model does have, these are the models that survive that use 3 variables, and then we have ones that use 4, and these tend to be very complex, and as it turns out, they're really overly complicated. We can generate our variable presence chart. We've seen that, and again, R is the big winner in our competition. D1 makes an appearance, perhaps because D1 is correlated with M1. We can look at variable combinations. These are combinations of variables that appear in the formula, and so this is where M2 and R appear together. This is where M1, M2, and R appear together, including our perfect model here. This is just R. So you're looking at different subsets of variables and seeing how well they're able to achieve both simplicity and performance. We can look at variable associations. And so again, here you're seeing that R and M2 and M1 form this nice little triangle. Let's do one other thing. Let's just select some variables. Supposing I only want to look at models that involve M1, M2, R, and D2, but not any of the rings. And we'll call this set restricted set. Save it. All right, and now let's use the restricted set. And now we can look and see what the quality of our models might be. We could look at the Pareto front plot among those models. You'll see there are fewer of them. My favorite model is still there. But again, this is a useful way of restricting the models under examination. And while here, in some sense, it's not quite so interesting because we actually found the perfect model, in other instances, it might be quite useful for you. There's tons more to Data Modeler and what you can do in the GUI, but this is my favorite plot just because I think it's beautiful and it compresses a lot of information. Basically, it's showing you in colors here how frequently these variables occur. This is what our legend here is telling us, so it's reminding us that R is the key to gravity, distance between the planets. But then it's also showing you the strength of various associations and telling you that, yeah, M2 and R really go together. And here now you can see, like, what does M2 connect with? And M2 is spending a lot of its effort connecting to D1, to M1, and to R, whereas D1 is spending its life connecting to R and to M2. So again, for some advanced work, this can give you a picture of the various associations between the data that might give you some insight as to what's really going on in your model. So this concludes our discussion of symbolic regression. In the first part of the video, I showed you how the concept of symbolic regression, how to use Data Modeler, and in this final part, I've tried to show you how a data professional might go about approaching analysis of a complex data problem. Thanks.